Hello everyone, welcome to my channel. Today I'll be discussing certain new examples from chapter number 15 of Clayden Book, Nucleophilic Substitution at Saturated Carbon. Now let us begin with two easy problems. So in the first one, on reaction with this one is thiophenol with a base sodium hydroxide. We know thiophenol is a nucleophile. Okay, it is a nucleophile, but it is not a very strong nucleophile. So in presence of a base sodium, that is here it has been given sodium Na plus OH minus sodium hydroxide, it is going to abstract this proton and a negative charge will be generated on the sulfur atom. Then it forms pH S minus. Okay, now it becomes a very good nucleophile as compared to the previous one. Okay, now it can attack here. Let me write it again. S double bond O Me means CH3 group. Okay, now it acts as a very good nucleophile, so it is going to attack at the carbon atom, and this bond will break and a negative charge will be in the oxygen atom. Okay, and we get S double bond O minus. This reaction is very easy, but if you don't know the concept behind this reaction, then you might make some mistake here. Okay, and since sodium plus was given here, so you can write here sodium plus. So this will be the product of the first reaction. Easy one, right? Now let's see the next problem. So there are two good leaving groups here, chloride or chlorine are two good leaving groups. Now the question is, which chlorine is going to leave from here? Now from these two chlorine atoms, if I leave this chlorine atom, if I remove this chlorine atom, then we are going to get COCl positive charge, and this positive charge cannot be stabilized, so this chlorine is not going to leave. Okay, so this cannot be happen. And if I remove this chlorine atom, then there will be generation of positive charge here, and the lone pair over this oxygen atom can stabilize this positive charge, and here it forms O double bond and a positive charge over the oxygen atom. Okay, then the next step is the lone pair over this oxygen atom is going to, here nucleophilic attack will take place here, and since I forgot to give this chlorine, there is chlorine is going to, this oxygen is going to attack here, and it will get neutralized and it will give the product as here OMe, H will be there, and here positive charge, and the chlorine atom here will remain as such. And in the next step workup will take place, this H plus ion will leave, and it will give us our final product as OMe and Cl. Okay, this will be our final product. Now let's move on to our next questions. Okay, now on this compound on reaction with this one is acid chloride and zinc chloride, what will be the product? We know zinc chloride is a Lewis acid. Okay, so what is its role in the mechanism? It can either remove the chloride or it can form complex with this one as like this. Okay, in both the mechanisms we are going to get finally the electrophile. Okay, now let us proceed via the first mechanism by removing the chloride. So it takes place as like this. There is acid chloride, the lone pair over this oxygen atom is going to get here and form a triple bond, and this, since chlorine is a good leaving group, it will leave and it will give us a linear structure because triple bond, right? So there will be positive charge, thus it is our electrophile. And in our next step, the lone pair around this oxygen atom is going to attack this electrophile. Okay, and this positive charge will be neutralized, and we get as O here with oxygen, this carbon will attach and double bond O. Okay, and this methyl group 2, and here positive charge will be established. Okay, then since a chloride was removed in the group, so this chlorine is again going to attack via nucleophilic substitution or locker, it will attack from this side or this side, same environment, right? So it is going to attack from one side, and this bond will break and it will get neutralized, and it will give our product as O, here carbon, here methyl double bond O, and here a chloride. Okay, this will give our final product in the reaction. Let us see this reaction. So it is a 7-membered ring, along with it sulfur. So what is this group termed as? It is thioester. Okay, on treatment with LiLH4, that is lithium aluminum tetrahydride, we can write it as AlH3. Here a negative charge will be over the aluminum, so it acts as a hydride donor. So hydride is going to attack in the carbonyl, the charge will go up and it will again come back, and a negative charge will be established in the sulfur atom, and we are going to get as, it is a 7-membered ring, it is above the plane, so it is S minus, and it is below, so it is chloride. Now our next chance is, since chloride is a good leaving group and it is anti to it, so this negative charge is going to attack here, and this group and chloride will leave, thus giving us our final product as, it will become above S, this will also above, so giving a 3-membered ring here. See our next question. So in this reaction, what are the products formed here? Okay, in the first step, this OH is above the ring. Okay, first is in it is tosyl chloride, and PY is pyridine. Pyridine is, this is pyridine, it has lone pair. Okay, so first of all, since pyridine acts as a base, so it will abstract this proton, and a negative charge will be reside in the oxygen atom. Okay, there will be a negative charge in the oxygen atom. Further, this negative charge is again going to attack in the tosyl group, and chlorine is a good leaving group, so it will leave, and it will give us OTS, tosylate. Now it becomes a very good leaving group. And in the next step, sodium acetate is given. Sodium acetate can be written as sodium plus CH3COO minus. In the next step, nucleophilic substitution will take place. This is going to attack. Where from it is going to attack? It is going to attack below the plane. Since it is above the plane, so it is going to attack below the plane, and this is a good leaving group. It will leave, and it will give us our product as below the plane OCOCH3. And the next step, K2CO3 in presence of methanol. So K2CO3 is a base. Let me write the full structure of K2CO3. O minus C double bond O minus K plus. It is a base and methanol, in presence of methanol. So first of all, this negative charge is going to abstract this proton, and the negative charge will be in the oxygen atom. Okay, then it acts as a nucleophile, and it will act in the attack in the carbonyl carbon. So this charge will come back, it will go and come back, and this bond will break. So we are going to get this one, and this negative charge over the oxygen atom, it will then work up, will occur, then it will work up, that is, it will abstract a proton from the solution, and we get the final product, this one. So from this step, from above the plane, we are getting below the plane, our final product. Now let's see our last question. So on treatment of this compound with a base, suppose a base is given, means what will be the first step? Firstly, the base will abstract an acidic proton. So where is the acidic proton here? So this hydrogen is attached directly with the electronegative atom, so it is the most acidic proton, so it will abstract this proton, and a negative charge will generate in the sulfur. Okay, it is above the plane, this oxygen is above the, this epoxide is from above the plane. Then a 3-membered ring is not that much stable. Instead, if there is a possibility of 6-membered ring, then it is more stable, and there is possibility in this reaction. So let us count 1 2 3 4 5 6. Since a negative charge is there and a 6-membered ring is also possible, so this negative charge is going to attack here, and this epoxide ring will open, and we get our product as the sulfur is attacking. It is above the plane, so it is attack below the plane. Attack below the plane. Okay. Then this was above the plane, so and a negative charge will be there, and after work up, this will abstract a proton, and this will be our final product of this reaction.